Jnanam Paramam Dheyam. Knowledge is supreme.
We are going to start with a revision of what we had done in the last class, and then we will go on and we will try and derive an expression for the probability of the higher level getting populated as a result of excitation by light. Okay? Shall we begin? Shall we begin? Great. So, let us remind ourselves a little bit about what we have discussed already about your time dependent perturbation theory. TDPT is time dependent perturbation theory. As you remember, we are now working with time dependent wave function capital Psi, and looks like I have gotten a little better at writing capital Psi with a little bit of practice. So, this is equal to the time independent space dependent wave function small psi multiplied by, but I will write the expression of phi anyway since we have done it once, e to the power I E t divided by h cross. Is that right? Is that right, or is there a minus sign? So, that is what I was saying. Do not assume that whatever I write is correct. Okay? You have to correct me wherever I go wrong. E to the power minus I E t by h cross, and the problem that we are dealing with involves two levels. One is L and the other is M. I can just write like this. Alright. So, what have we said? We have said that when there is no light, the Hamiltonian of the system is the unperturbed Hamiltonian, and the wave function of the system is capital Psi L. Okay? Then we said, what happens when I turn on the light? In presence of light, and one of you asked the question, how is the light on or has it gone off? The answer is light is on. We are taking it as an oscillating electric field, as we will discuss shortly. So, of course, there is an oscillation and all, but the light is on. What we do is at some 0 time, before the light is turned on, the system is described by a wave function capital Psi L, then we turn the light on and keep it on. Okay? We have not turned the light off yet. When we turn the light off, it becomes a different ball game altogether. So, in presence of light, the system is described by a wave function capital Psi, which is equal to CL multiplied by capital Psi L plus Cm multiplied by capital Psi M, and we are working with initial time t tending to 0. So, this CL tends to 1 and Cm tends to 0. This is an approximation that we are going to use shortly anyway. So far so good. And then the other thing, and this is where I had made a mistake. In presence of light, what is the Hamiltonian? Hamiltonian is H0 plus some perturbation term H1, yeah. Right, we are working within the ambit of first order perturbation only, small perturbation, a first order is good enough. Okay. And today we are going to write an expression for this perturbation, and that is, we will write it as minus mu x E x. To start with, we are going to confine our discussion to one axis, x axis only. So, we are talking about plane polarized light, right, and that is what it is. So, mu x is the x component of the dipole moment of the molecule. So, we are considering the perturbation to be an electrostatic interaction between the electric dipole of the molecule and the oscillating electric field associated with light. Does that mean that there is no interaction between the magnetic field and the magnetic dipole? Then it does not mean that. Does that mean that there is no interaction between the electric field and magnetic dipole? No. All it means is that we are starting with the interaction that is largest. Electric field, electric dipole, this interaction is the largest. So, if you have learned this solute solvent interaction, you might remember that the most important interaction is ion dipole, considering a dipolar solvent, followed by dipole dipole interaction, followed by induced dipole interaction, and so on and so forth. So, different interactions are there, some are large, some are small. We are focusing right now on the largest interaction. In a later stage of the course, there will be occasion to talk about weaker interactions, right, but this is only the starting point. And how do I write Ex? Is this part of the board visible from the back? Can you see, read this? Ex is written as 2Ex0 cos 2 pi nu t, where nu is the frequency of light. Okay. We are going to use this expression today and we will see how this gets modified. But before that, let us redo what we had done in the last class and get an expression for time derivative of this coefficient dCm. Okay. We will do it quickly. So, in presence of light, your Schrodinger equation should be something like this. The Hamiltonian, as we have said already, is the uncorrected Hamiltonian first plus the first order perturbation term. That Hamiltonian operates on the wave function. What is the wave function? Tell me. What is the wave function when light is on? Cl into capital psi L plus Cm into capital psi M. We have to consider both the states. Cl into capital psi L plus Cm into capital psi M. I am trying to write the time dependent Schrodinger equation. So, can you tell me what the right hand side will be? Minus h cross by I multiplied by del del t of this whole thing, minus h cross by I del del t of Cl capital psi L plus Cm capital psi M. And before proceeding further, we need to remember one thing, that this Cl and Cm, these coefficients are functions of time. Okay? These coefficients are not independent of time. At time t equal to 0, Cl is exactly equal to 1, Cm is exactly equal to 0. As the time proceeds, the value of Cl decreases from 1, value of Cm grows from 0, right. But we are working under the approximation that our discussion is confined to initial time, where Cl deviates not too much from the value of 1, Cm deviates not too much from the value of 0. Please remember this. This is usually a source of confusion, because what we often think when we read this part is that we are saying Cl is equal to 1, we are saying Cm is equal to 0, then how do we even talk about dCm dt? Please remember, we are not saying Cl equal to 1, we are not saying Cm equal to 0. All we are saying is that the deviations of Cl and Cm from the initial values of 1 and 0 respectively are not too much, but deviation is there. Otherwise, what are we talking about? Okay, right. So, when we expand, what happens? On the left hand side, what are the first two terms? H0 Cl multiplied by, maybe I will do it, Cl H0 capital psi L plus Cm H0 capital psi M plus Cl H first capital psi L plus CM H first, capital psi M, and the right hand side is Cl del capital psi L del T plus Cm. Oh, who is going to write this minus H cross I? I always forget that. I will write it once, safe chalk, minus H cross I multiplied by Cl del T of capital psi L, Cm del T of capital psi M, plus, this is the important part, capital psi L dCm dt, right, dCl dt plus capital psi M dCm dt. Okay, so far so good, alright. Am I allowed to write dCm dt or do I have to write del Cm del T? Was there a yes or was there a no? For both? Then we can write dCm dt, very good. Okay. Now what happens? Look at this term and look at this term, they are actually equal to each other. That is your time dependent Schrodinger equation for capital psi L. Look at this term and look at this term, time dependent Schrodinger equation for capital psi M just multiplied by Cm. So they cancel off. Okay. We are left with, do not forget that H cross by I. This is what we are left with, right? Is that right? Then what did we do? We said there is no point trying to talk about dCl dt and dCm dt both at the same time, because it is not as if they are uncorrelated. dCl dt and dCm dt are correlated. dCl dt is the rate of disappearance of psi L, the state associated with psi L. dCm dt is the rate of production of the state associated with psi L. It is enough if you work with 2, and if you work with 2 it is complicated anyway. So, we want to eliminate one of the terms. We just decide that we are going to work with dCm dt. I want to eliminate this. What is the best way of eliminating the first term? Left multiply by the complex conjugate of capital psi M and integrate over all space, right. Then what will happen? This is going to vanish because capital psi L and capital psi M are orthogonal to each other. Okay. Let us do that. When I do that, this is what I get. On the left hand side, I get Cl integral capital psi M H1 capital psi L integral over space or time or both? Space, only space, not time. That is what bracket means, right? Space plus Cm integral capital psi M H1 capital psi M is equal to, I can just write it there, is equal to minus H cross by I dCm dt. We have already discussed why on the right hand side we have only one term, because the other term vanishes. Is it okay now? There is a minus sign because of ineffective erasing of what was written earlier, I think, or maybe not, whatever, but this is correct. Now we are okay? Okay. So far so good? Alright. What is the next thing that we have to do? Now we use our approximation. In fact, so far have we used any approximation? No, right? So far it has been an absolutely exact treatment. Now we use that approximation of ours, that this Cl is more or less equal to 1, Cm is more or less equal to 0. alright. So, what we do is we put this to 0 and we erase. So, finally, you are left with dCm dt is equal to, what do I put this to be? We put this to be 1, right, is equal to minus I by h cross. Now, I can simplify this a little bit, can I not? Because integral is over space. So, I can keep the space dependent part of the wave function inside the integral and I can bring the time dependent part out, right. So, I can write it like this, integral over space psi m h1 psi l. Please note, psi m and psi l written here are different from what are written here. This is small psi, these are small psi's, these are capital psi's. So, these are product of space dependent as well as time dependent part. These are only the space dependent part, okay, and the time dependent part comes out. What does the time dependent part turn out to be? Exponential, what will it be? I Em minus El T divided by h cross, is that right? Yeah. Okay. Well, in the textbook it is written as minus I multiplied by El minus Em. So, it is the same thing, does not matter. So far so good. So, this is where we had reached. Now, we are going to use this and we are going to proceed with the next part of the discussion. Is there any question up to this? Up to this we are all good. Now, you have to be careful because now is where our opinions seem to differ.